Good to go, Jim.
Okay, we're going to begin our proceedings this afternoon with an introduction by our colleague Michael Morgan, who's a professor on leave from the Department of Atmospheric and Oceanic Sciences, and he's going to introduce today's speaker. So Michael, go right ahead.
Thank you, John. I'm delighted to introduce today's colloquium speaker for our Ph.D. defense, Ms. Chen. I regret that I can't formally be there or physically be here today, but I thank the members of the committee and the department for their supportiveness and direction in the last year of this work. I first worked with Noah in spring of 2018 as a visiting, she was a visiting undergraduate student from Nanjing University's Information Science and Technology, or UWS, when she took Atmospheric Ocean 611, jointly taught by me and Professor Hitchman. Following that spring semester, she joined my lab as a summer undergraduate researcher and made her first strides in learning about the WRF model and its advent. She returned to NOST in fall of 2018, where she then graduated from the School of Hydrology and Water Resources with a degree in Atmospheric Sciences and Hydrometeorology in June 2019. While there, she started her graduate studies in our program in 2019, but didn't arrive on campus until early 2020 due to some visa processing delays. While waiting for her visa to clear, she was able to gain additional research experience at the Shanghai Typhoon Institute, which led to a publication. Her arrival early in 2020, just in time for instruction to transition to remote, was not the greatest of timing. The last 3 years of this pandemic have been a challenge for all of us, but imagine traveling around the world to begin your graduate studies, far removed from the direct personal embrace of friends and family, uncertainties in their welfare, and when you might, wondering when you might next get to reconnect with them. Beginning a new chapter in your life without those supports is a daunting set of circumstances I can't fully appreciate. Couple that with the unplanned departure of two of your committee members, but however, through it all, Noah's determination, perseverance, curiosity, skill, and scholarship has led her to this day. Noah Chen is a resilient individual and an impressive scholar. A few additional items you might not know about her: she loves to cook and does it quite well. And she was a point guard for her university's women's basketball team for a couple of years. She now has a postdoc research opportunity lined up with Professor Stephen Cavallo at the University of Oklahoma, where she'll be studying the critical mechanisms that determine the location, strength, evolution, and characteristics of Arctic cyclones and Chocoball's polar vortices, and their potential for influencing sea ice breakup and decline. The work she's about to present from her dissertation is impressive. It represents a significant extension of a set of tools to interrogate adjoint sensitivity fields for synoptic case studies, and an important explication of the notion of adjoint sensitivity to imbalance. I look forward to the presentation, development, and application of adjoint sensitivity to potential vorticity and unbalanced flows for the WRF model. No, the floor is yours.
Thank you so much, Michael. Sorry, I need to share it on Zoom as well. What about that? All right, as Michael mentioned, I'm going to talk about what I've been studying for the, is it possible to, I'm not quite familiar to Zoom yet. I'm going to talk about what I've been focusing on, which is the adjoint sensitivity to potential vorticity and the unbalanced flows in the WRF model. This work is supported by Sims Bell Smith Scholarship and NSF Award. So first, what do I mean by sensitivity? Imagine we're using numerical weather prediction to do the weather forecast, and the perfect forecast would be the one that has no forecast error. If there's a huge error in your forecast, then you might want to know what caused the error to grow. And the sensitivity analysis would offer us to see which variable that caused the largest error, and the variable that causes large error would have the largest sensitivity. Another application of it would be in the target observation. We know that the initial condition error can grow dramatically with a highly nonlinear model. and improving the initial condition with targeted observation in the most sensitive area in mission like Hurricane Hunter recon mission would allow us to improve the weather forecast much better in such damaging events. Another application is we can use sensitivity study to understand dynamical process underlying the storm intensification. It will show us which variable leads the storm to intensify among all the possible underlying dynamical processes. So in general, we define the sensitivity x hat as the partial derivative of response function r to the state vector x, where the response function r could be our forecast error or the storm intensification or storm intensity that can be measured by the central pressure, precipitation rate, or surface wind. The state vector is a combination of wind, pressure, temperature, and moisture. Using the Taylor series expansion, we can write the change in response function dr as the product of the sensitivity gradient dr dx and multiply that with the perturbation dx. There are two major ways to do sensitivity analysis. The first one is run the ensemble sensitivity, in where you perturb a variable and let the model run for several times and see if there's any change in the final forecast error or in the response function. If the change is large, that means the variable is very sensitive. If there's no change, then that means the variable is not sensitive at all. The next method involves the adjoint model, and in the normal model that we run a model, nonlinear model forward, and has the initial condition as input, let it run forward, and it gives us the state vector at each time step. The response function is going to be a function of the final time state vector. Then we can linearize the nonlinear model along the trajectory, and that gives us the tangent linear model showing the blue line here. So the tangent linear model is linear around the trajectory, and it takes in the perturbation input and run it along the trajectory, and it gives us the perturbation at each time step as the output. The adjoint model is the transpose of the tangent linear model. It runs the model backwards in time and takes in the adjoint forcing, which is denoted by the sensitivity gradients at the final time. And then the adjoint model outputs the sensitivity gradient at each previous time step. So it's all very abstract concepts. I'm going to show you what sensitivity actually means in the case of Hurricane Ian. So Hurricane Ian caused heavy precipitation, flash flooding, damaging wind, and storm surging in Cuba, Jamaica, and Florida during its lifetime. It has also ruined our first 2 weeks of weather challenge forecast last year. Right. So the time period I'm going to focus on is going to be the rapid intensification period, which lasts from September 25th, 18Z to 26th, 18Z, where it deepened from 100,003 hectopascal to 976 hectopascal. So you can see for the onset of rapid intensification, we have the storm sitting quite warm SST exceeding 30 degrees Celsius with very low vertical wind shear and a pretty sufficient low-level moisture. The warp model is run with full physics for 24 hours initialized by GFS free analysis data under 24 kilometer resolution on 41 vertical levels. The warp produced a Hurricane Ian to deepen from 999 hectopascal to 980 hectopascal here, but you can see the intensification rate is quite similar to what's happening in reality. For the adjoint analysis, we're going to set the response function as the minus dry column air enclosed by 1004 hectopascal contour, which means we want to deepen the storm in this green area at the final time, sorry. The adjoint analysis is carried out by the warp plus model and only run with the dry component. So remember what we mean by adjoint sensitivity. is that how can we perturb the model at each time step to lead to the storm to intensify at the final time. On the right, I'm showing sensitivity to winds in bars and to temperature in shading at 900 hectopascal. This tells us that we want to have more warm air in the core of TC for Hurricane Ian to intensify at the final time, and the cyclonic wind sensitivity tells us we want to add more cyclonic winds around it for it to deepen at the final time. So, knowing the sensitivity to winds and to temperature is great, and previous study has been focusing on the interpretation of individual sensitivity variables. But is it possible that we can combine the sensitivity to winds and to temperature together into a variable, like we combine winds and temperature into a unified diagnostic variable called potential vorticity? So that's everything I've put in my dissertation. I'm not going to show all of this here. Instead, I'm going to select these questions and go through it. First, I'm going to derive the sensitivity to PV and to geostrophic imbalance and provide the interpretation of them. The second, I'm going to show you how they are different from each other in the case of Hurricane Ian. Finally, I will briefly prove some application of sensitivity to PV in other fields. Before we dive into the derivation of sensitivity to PV, let's have a quick review of what PV is. So potential vorticity, it is a combination of relative vorticity and static stability. It is known for its characteristic of conservation and invertibility. PV is conserved for a inviscid and adiabatic flow. Ertel PV is conserved on isentropic surfaces, and quasi-geostrophic PV is conserved on isobaric surfaces. For its invertibility, it states that given a distribution of PV within a domain and a balance constraint, one can recover the winds and temperature fields around it. But what do we mean by the balance constraint here? We're all familiar with all the balances in the atmosphere. There's geostrophic balance, which is the balance between the pressure gradient force and the Coriolis force. And there's also gradient wind balance that adds another component of centrifugal force to it. The nonlinear balance, which not all of us are familiar with, takes the forms of using string function and geopotential. And it's derived by ignoring the divergence related term in the divergent equation. If we ignore the Jacobian term here and assume f is constant and cancel out the Laplacian on both sides, and that gives us back to the geostrophic balance in the form of perturbation string function and geopotential. The prime here denotes the perturbation. Having the definition of PV and balance, we can find sensitivity to PV following Arbogast 1998. Here Q means PV and A means imbalance, which is the deviation from geostrophic balance. Phi prime and psi prime are perturbation string function and geopotential. L's and B's are operators that calculates Q prime and A prime from psi prime and phi prime. Taking the adjoint of this set of equations gives us this. If we want to find the sensitivity to PV, Q hat here, remember we define sensitivity, we can simplify sensitivity as a hat here. We need to know the sensitivity to string function and to geopotential, which can be calculated from sensitivity to winds and sensitivity to temperature directly from the Whorf adjoint output. We also need to know the adjoint of operators L's and B's, and the star denotes the adjoint of these operators. Luckily for us, in all our cases, that the operators are all self-adjoint, meaning that the adjoint of these operators are the operators themselves. To find sensitivity to QGPV, we need the definition of QGPV perturbation and the geostrophic balance. We also need to find what the operators L's and B's are. So for example, L phi here is just del squared, L psi here is del squared, L phi here is second order derivative in vertical direction. B psi here is just simply 1, and B phi here is minus 1 over f. If we denote the QGPV operator as P, we can find the sensitivity to QG hat here in a form like this. And that's what I did for my research chapter 1. As you can notice, there is also a byproduct of this, sensitivity to imbalance. Exploring what does imbalance mean and the interpretation of sensitivity to geostrophic imbalance is what I did for my research chapter 2. Finally, to find the sensitivity to Ertel PV, we need the definition for Ertel PV, of course, and use nonlinear balance. We linearize the above equation into this form, and the pi here notes we're calculating Ertel PV in the x-inert coordinate. The sensitivity to Ertel PV QE hat can be easily solved using this equation, while phi p here on the left is an expression like this, and UP prime, UP on the right is an expression like this. So it's much complicated than sensitivity to QGPV. And that's what I did for my chapter 3. Now we've derived the sensitivity to QGPV and to geostrophic imbalance. How do we interpret them? Here is the perturbation QGPV. If we take the adjoint of those, so we have the maximum adjoint sensitivity to QGPV in the middle. We see that the Q hat dy is negative along the positive y direction, and that gives us U hat to be negative and pointing to the west. Similarly, the Q dx is also negative along the positive x direction, and that gives us V hat here positive and pointing to the north. It is easy to see that around a positive sensitivity to PV, you have a cyclonic wind sensitivity surrounding it. Again, taking the vertical derivative of Q hat, we see that Q hat decrease with increasing pressure. That gives us theta hat is less than 0, and a positive theta hat above it. If you remember that given a PV, we can invert a cyclonic winds around it, and warm temperature above and cold temperature below, you will notice two things. The first thing is that we can combine sensitivity to winds and temperature into a variable called sensitivity QGPV. And around a positive sensitivity QGPV, there's going to be cyclonic winds around it, cyclonic wind sensitivity around it, with warm temperature sensitivity above and cold temperature sensitivity below. Second thing is that it's possibly valid to treat sensitivity as putting a small perturbation into the system at instantaneous time. Next, we're going to explore the notion of imbalance. Remember, this is the geostrophic balance here, or in the form of perturbation stream function and perturbation geopotential in this form. A, imbalance, is defined as the difference between these two terms. 1 over f phi prime is going to be the geostrophic stream function. If we only focus on the contribution of psi hat, psi prime here, with a positive, with a greater than 0, we would have a surplus of stream function that deviates from the geostrophic balance, and that positive phi hat would give us anticyclonic winds around it. If A is negative, then we can say there's a deficit of stream function, and that leads to a cyclonic wind perturbation around it. If we say that it is the geopotential that deviates from the geostrophic balance, then with a positive A above, we can say that there is a deficit of geopotential above, and that will bend the isobaric surface down. If we have a negative A below, that says there's going to be surplus of geopotential perturbation, and that's going to bend our isobaric surfaces up. in between these two isobaric surfaces, the thickness is much thinner than the other places, and that is correspond to a cold temperature anomaly here. And vice versa is for the configuration of negative A above and positive A below. Any questions? Since we define A as the deviation from geostrophic balance, it's natural to compare it with the ageostrophic wind. If we take the curl of A, that gives us this expression, and we notice that the first term is going to be the purely rotational wind, and the second term is just going to be the geostrophic wind, which is also non-divergent. So we can say that the unbalanced winds associated with the imbalance, and unbalanced winds are noted by the subscript I here, is very similar to the ageostrophic winds, but they don't have the divergent component. We can show that with example in a mid-latitude cyclone case. Here I'm showing the orange, here is showing A as positive, purple here is showing A as negative. The ageostrophic winds are in black arrow, and the unbalanced winds are in red arrow. So near the surface at 900 hectopascal, near the storm center, we see that the ageostrophic winds has much inward components than the unbalanced wind pointing into the storm center. And at the jet level, at 300 hectopascal, you can see at the jet entrance region that the ageostrophic winds has more of a component pointing equatorwards than the unbalanced wind. These two examples shows exactly what we derive in the equation, that is the ageostrophic winds and unbalanced winds are quite similar, but the unbalanced wind doesn't have the divergent component. So I've explained what I understand of the geostrophic imbalance is. Let's examine what's the sensitivity to it. Remember, we have the expression for sensitivity to geostrophic imbalance A hat as a combination of sensitivity to stream function, psi hat, and sensitivity to geopotential phi hat. And the QGPV operator here can be approximated as three-dimensional Laplacian operator. Note, these three operators are all taking second-order derivative, so that means that we can treat A hat and psi hat has the same sign, and A hat and phi hat would have the opposite sign if we look at them individually. So if we only focus on the psi hat and have the configuration of having positive A hat above and negative A hat below, that would say we would have a positive psi hat above and negative psi hat below. Remember, we can treat a sensitivity as putting a small perturbation into the system. That would mean that we would have anticyclonic wind sensitivity around this positive psi hat and cyclonic wind sensitivity around this negative psi hat below. With the Coriolis force, F would torque the above anticyclonic wind sensitivity into a sensitivity of convergent above, and it would also torque the cyclonic wind sensitivity into a sensitivity into divergence below. And with the convergent above and divergence below, it would lead to a sensitivity to downward vertical motion in between. If we only focus on the contribution of geopotential here, again with the positive configuration of positive A hat above, negative A hat below, that would give us a negative phi hat above and positive phi hat below. The negative geopotential anomaly would bend isobaric surface down again, and the positive one would bend isobaric surface up. And in between is going to be correspond to a cold temperature sensitivity. And invoking the geostrophic adjustment theory, we will want a sensitivity to downward vertical motion to bring adiabatic heating to offset the cold temperature anomaly or cold temperature sensitivity. Before I end the part of interpretation, I want to note, similar to the PV invertibility, given a distribution of sensitivity to PV, and sensitivity to imbalance, we can also invert a balanced sensitivity to winds and to temperature. They are in geostrophic balance, and unbalanced sensitivity to winds and to temperature from them. These two tools allows us to separate the balanced and unbalanced sensitivity fields from the Whorf adjoint original output. So far, I've showed the derivation of sensitivity to PV, to geostrophic imbalance, and how to interpret them. Next, we're going to apply them to the Hurricane Ian and see how they're different. In the middle, I'm showing the storm center with the PV contour here. On the left, I'm showing the sensitivity QGPV at 850 hectopascal. In the middle is sensitivity to geostrophic imbalance, and on the right is sensitivity to Ertel PV. We can see that for both sensitivity to QGPV and to Ertel PV, positive PV sensitivity is required, or that means we want to put more PV near the storm for the storm to intensify at the final time. Sensitivity to imbalance is in general negative at 850 hectopascal. Compare the sensitivity to QGPV and to Ertel PV, we see it's obvious that sensitivity to QGPV has a much broader spatial distribution, while sensitivity to Ertel PV has more detail, such as the scattered feature on northeast to the storm center. We can also see that, like sensitivity to QGPV, sensitivity to Ertel PV has its maximum to the southeast of the storm center. But unlike the sensitivity to QGPV, sensitivity to Ertel PV say that in this region, right next to the storm center, the storm intensity is not actually sensitive to the PV. Next, we're going to compare sensitivity to QGPV and sensitivity to geostrophic imbalance. We note that the positive value in the sensitivity to QGPV overlaps the sensitivity to negative sensitivity to imbalance in almost the same region. Remember, with the positive sensitivity QGPV, we would have a positive cyclonic sensitivity surrounding it, and it's in geostrophic balance. Again, with the negative imbalance, it will also invert to a cyclonic wind sensitivity around it. And that means, in our case, that the sensitivity to winds is super geostrophic for the Hurricane Ian at lower level. Here I'm showing the sensitivity QGPV to geostrophic imbalance to Ertel PV at 500 hectopascal. You can see for the sensitivity QGPV, the sensitivity maximum is always tracking the storm center, while for the sensitivity to Ertel PV, the largest sensitivity starts to the south of the storm center and doesn't converge to the storm center until near the final time. The sensitivity to imbalance is quite scattered at 500 hectopascal, unlike at 850, where you have a broad region of negativity. So again, it's just compare them at the initial time step. Sensitivity to QGPV is centered on the TC itself, and sensitivity to Ertel PV is much to the south of the TC center. You might also notice there's a negative sensitivity PV here, and I don't have a quite good explanation for it yet. Next, we examine the sensitivity QGPV to geostrophic imbalance and to Ertel PV at 200 hectopascal. You see for the sensitivity to QGPV, there's a general negative pattern at the upper troposphere, while the sensitivity to Ertel PV and to geostrophic imbalance, the features are quite scattered. For a matured hurricane at the upper troposphere and the storm outflow level, it is characterized by small or negative PV value here. And sensitivity QGPV says that we want to lower the PV even more to the east of the storm for the storm to intensify. Having a negative PV here would lower the inertial stability and allows the outflow, radial outflow of the hurricane to expand much easier at this level. Compare the sensitivity to Ertel PV and sensitivity to imbalance, we see that they have almost similar feature at this region. But sensitivity to Ertel PV can also resolve some feature that we see in sensitivity to QGPV here. That suggests sensitivity to Ertel PV is able to combine some features of sensitivity to QGPV and to geostrophic imbalance. Next, I'm showing you the sensitivity to winds and to temperature from the WRF output in the middle. Those one inverted from sensitivity QGPV on the left, and these two fields, the sensitive winds field and to temperature field, should be in geostrophic balance. On the right, I'm showing you the sensitive to wind and to temperature field inverted from geostrophic imbalance, and in the bottom, it's the wind and temperature sensitivity field inverted from the sensitivity to Ertel PV, and they should be in nonlinear balance. We see at the initial time at 850 hectopascal, both sensitivity to QGPV and to Ertel PV is able to resolve the cyclonic winds sensitivity pattern from the WRF output, and compare the sensitivity to QGPV and to geostrophic imbalance, they're both able to resolve the temperature sensitivity from the WRF model, while the warm temperature sensitivity resolved from sensitivity to QGPV is more concentrated to the storm center itself, and the temperature sensitivity inverted from geostrophic imbalance exists at the broader region. You might notice that the sensitivity to Ertel PV inverts a negative or cold temperature sensitivity at lower level. If we take a cross-section of it, you might see here in the contour it's showing QE hat, and it has a maximum here at this level. Above it is going to be a positive temperature sensitivity, and below it is a negative temperature sensitivity. Although this inversion does not quite conform with the WRF output, it fits our understanding of having a positive sensitivity to PV, where you have a positive temperature anomaly above, sensitivity above, and cold temperature sensitivity below. So, I've shown you the difference of sensitivity Ertel PV to QGPV and to geostrophic imbalance in the case of Hurricane Ian. Next, we're going to quickly see some application of balanced sensitivity fields and something about PV perturbation. This is what you got from the WRF output, from the original WRF output. You see a lot of gravity waves here, and they would bounce back from the simulation domain. The field I'm showing is 500 hectopascal sensitivity to potential temperature after 6 hours of integration in the adjoint model. This is pretty ugly, and it contaminates our adjoint sensitivity analysis, and it might even lead you to think that putting more cold air over Cuba would lead the Hurricane Ian to intensify at the final time. So we think that this gravity wave generates because there's a mismatch between sensitivity to wind field and sensitivity to temperature field. And the process of geostrophic adjustment, even in the adjoint model, would lead to the emission of gravity wave. So in order to avoid the adjustment process, can we feed it, or feed the adjoint model with the adjoint forcing that is already in balance? To do that, we run the forward model first, set the response function and find the adjoint sensitivity to it, and let the model run backwards for the first time. Then we're gonna take a sensitivity gradient that is close to the end time, calculate the sensitivity QGPV, and then invert the balanced sensitivity fields that are in geostrophic balance and feed them as the adjoint forcing and run the Adjoint model for the second time to get the result. Remember, that's what the ugly picture that we see from the first Adjoint model, and that's what we got from the second run of the Adjoint model. You can see the field is much clearer and much easier to interpret. It doesn't throw any cloudier sensitivity into your model domain that might indicate you can intensify the storm with cold temperature anomaly. So the next question I want to answer is that, can one approximate approximate sensitivity to PV with PV perturbation? Previous adjoint studies has been using PV perturbation as an approximation for sensitivity, adjoint sensitivity to QGPV. They think that in their optimal perturbation experiment, because the initial condition that they put in is proportional to the adjoint sensitivity, and then they would naturally think that the perturbation of PV, the PV perturbation, which is the PV difference from the perturbed run, between the perturbed run and control run, would also be proportional to the sensitivity QGPV at each time step. But is that true? To investigate that, I run the Hurricane Ian with an optimal perturbation intended to weaken the storm. So on the left, I'm showing you the difference in Ertel PV from the perturbed and control run shaded. On the right, I'm just showing the sensitivity to Ertel PV. The contour here on the right is just the positive and negative value on the left figure here. You can see clearly that they do not evolve quite similarly, except at the first time step. So I think it's safe to say that PV perturbation isn't actually a good approximate of sensitivity to PV. So to conclude, we've shown the derivation of sensitivity to PV and to geostrophic imbalance. We provide the interpretation of these variables in these figures, and most importantly, sensitivity QGPV is able to combine sensitivity to winds and to temperature into one unified diagnostic variable. For the research question 2, I've shown the difference of these sensitivity QGPV to Ertel PV and to geostrophic imbalance in the case of Hurricane Ian. And we see that sensitive QGPV is much broader, so sensitivity to Ertel PV has much more detail. And finally, I've shown you the case that we can filter out the gravity wave pattern in the adjoint sensitivity fields with the balanced adjoint forcing, and prove that PV perturbation isn't actually a good approximation of sensitivity to PV. For my future work, I would like to add balanced moisture variable into the balanced adjoint suite. Previous study have showed that the sensitivity to PV and sensitivity to moisture, or PV perturbation and moisture perturbation, are co-located either in the mid-latitude cyclone case or in the tropical cyclone case. And having a balanced moisture would help adjoint sensitivity analysis in the tropical area, which follows the weak temperature gradient balance to be much precise. Another thing I want to do is to study the nonlinear sensitivity from the neural network, which provides a technique called back propagation that is quite similar to adjoint technique. Right. I want to give my acknowledgement to Dr. Michael Morgan for his mentorship. John, thank you for stepping in at the final time and save the day. And thank you to Brett, Greg, Angel, and Leslie, and Dr. Kim for your help and support. To Pete, who always maintain the system and keep everything in order and often always here to offer help. To everyone in the high impact weather group for your feedback and support. Everyone, the graduate students and undergraduate students in the department, my roommate Alicia and her dog Tank, and my friends and family in China. So thank you very much, and I'll take questions from here.
Okay, thank you very much, Nuo. Let's have questions from the general audience, and then the committee members will meet privately with Nuo afterwards. So any questions from the general audience, non-committee members? Zoe?
I know. Great
Yeah.
talk. Super interesting to see how it's changed, evolved. I was curious, you showed the difference in the sensitivities that you filtered out. Like, I'm assuming that was 3 hours from the response function time.
Yeah.
How did the sensitivities patterns change if you go to the initial time sensitivities? Do you still see a filtered pattern, or do you see a similar distribution with that filtered field?
I think you are familiar with the result that the gravity waves will be dampened at the initial time. And I don't know, but when it integrates backward with the balance forcing and with the original forcing, the initial fields of sensitivity are sometimes different. So there might be some impact from the gravity wave pattern at the final time that still have its projection in the initial time.
Brad?
This is kind of a naive question, but so between the QG PV sensitivity and the Ertel PV sensitivity, there's really different magnitudes.
Yes.
Does that imply more sensitivity, or since it's a perturbation is the magnitude? What can you say about the magnitude? Some of those is like 10 to the 4th, and like 10 to the 4th versus 10 to the 6th.
So QGPB has a scale, not the sensitivity, but the QGPB itself has a scale of 10 to the 5th, minus 5th. So if you put that in the denominator, it will be about the scale of 10 to the 5th.
Okay.
And Ertel PV has the scale of minus 10 to the 6 to 7 because it has an extra term of you have density in the bottom.
Okay. So the fields themselves are different.
Yeah.
Thank you.
But the wings that inverted from sensitivity to QGPV and to Ertel PV are on the same scale.
Okay. Thank you.
There's a question online too.
Oh, great.
Also, Bailey and Srinath said, nice talk. And Rosa and Rudra. So Matt Hitchman asked, he also said, nice job. He said, I was wondering how to understand the clockwise inward sensitivity pattern at 850 when the inward flow is counterclockwise. I think I said that right, because he typed it wrong the first time and corrected himself.
Quite hard to. I think if I understand that correctly, it's the trajectory that advanced the sensitivities into the final time. So could you repeat the question again?
The question was, I was wondering how to understand the clockwise inward sensitivity pattern at 850 when the inward flow is counterclockwise.
The inward flow.
Is that maybe in reference to the extratropical case? Because that's the only time I think we saw
Okay.
Yeah, I'm not-
unbalanced winds and the ageostrophic winds, but I don't know. Yeah, that one.
I know you're a little behind, Matt, but we're wondering if this is the figure you were questioning. Well, maybe we can move on to another question and wait
Yeah,
for
okay, we'll wait
if
for
he
response
comes back.
to that.
Sorry,
There's a
Matt.
delay between the
Okay.
chat.
I have a feeling it might be this panel, but I don't know. Any other questions while we wait? Okay, well, I guess we're in the uncomfortable position of waiting. Yeah.
I was wondering, in your delay equation for the sensitivity, would there be anything that would cause your equation to break down? Like, or would there be cases where you wouldn't want to use it?
There are so many things.
Okay.
So I didn't do the sensitivity Ertel PV at the boundary because there's so many topography there, and to derive sensitivity to Ertel PV, you have these basic states here, and these basic states are from reanalysis data, and there's so many topography can goes into it that doesn't actually resolve, and that breaks my SOR algorithm for solving sensitivity to Ertel PV. But sensitivity QGPV isn't quite alike. I think it also resolved the negative sensitivity QGPV there. So,
Thank you.
yeah, thanks so much.
Okay, I did hear back from Matt. He said he was talking about the Ertel's PV sensitivity at 850 for Ian. And I think I understand better. He was talking about the clockwise inward sensitivity pattern when the inward flow on that was counterclockwise.
What flow?
Is it like tilted? It kind of looks counterclockwise, but it's not. It's like the kind of form.
You're right.
You've suggested.
I don't know. These are just instantaneous images of sensitivity fields at a level. There's no flow involved.
Yeah.
Right, that's how I'm looking at this. I don't understand.
I
flow.
would just say that because it's he used clockwise and counterclockwise. More familiar with cyclonic than anti-cyclonic, but I think here the wind is cyclonic around the TC center, and that background wind will advect the sensitivity to Ertel PV inward into the storm into the final time.
There's a question in the survey.
Oh, okay. Sorry.
Hopefully that helps, Matt. Otherwise, maybe you can touch base with her individually offline.
Form mechanism dictates the structure of sensitivity relative to winds. I think that's Michael's answer to Matt's question.
Ah, okay.
Right, the structure of the sensitivity to PV often tilts or leans up shear relative to the wind shear around the cyclonic structure. So, the sensitivities are identifying structures that are going to amplify by taking advantage of the shear flow. And so the fact that they kind of are going opposite the cyclonic winds around the tropical cyclone, really they're configured so that they can lean against the ambient shear or the basic state shear in the tropical cyclone. So that's how they can extract energy and grow. But I guess someone else could perhaps continue that explanation.
Anything else online, Pete? And Myra has a question.
Can you talk about how you set up the model? I don't think you touched upon that.
You mean just the work model?
Yeah.
Find the slide. Yeah, just using the for physics is 24 kilometer resolution on 41 vertical level.
And how did you initialize it?
With GFS reanalysis data, the final FNL.
So by reanalysis, you mean NOAA reanalysis?
Yes.
Any other questions? Yeah, Gerald.
Is there a way you can use your results to like make the forward simulation better, right? Because you're finding out like how like your original simulation shows that like it didn't deepen as much. Like, is there a way to feed back your results into the model itself to make it better, or how do you use that? How do you think?
Okay, I think how do we use sensitivity to PV is it serves as a diagnostic tool for us to understand the underlying dynamical process beneath the case study. It is possible, to run the model better, I think it still needs you to have a low resolution, first of all. Sorry, not low resolution, but higher resolution with smaller smaller horizontal interval. But it also depends on which reanalysis data you choose to feed into your data, right? And of course, you can perturb the initial condition and lead it to a more realistic case, or you can use the observation and assimilate them into your initial condition, like with technique as 4D bar or 3D bar, and that will lead to a model that produces a much better result. And I should note that the 4D bar also has a adjoint component to it that brings the observation back to the initial state.
Okay, if there's no other questions, and I guess, well, you can get in contact with Matt in another time. If there's no other questions from the audience, let's give another round of applause to Chen Nuo, and then continue.